is Laura Gutierrez Funderburk, and in this talk, I'd like to share with you some of the cool work that I've done with Python and Jupyter Notebook. I work as a full-time data scientist for Cybera as part of the Callisto project, and I like keeping myself busy on the side. I like using every chance I get to work with Python and Bash scripting, and I recently joined the Vancouver PyLadies group. So I'm just going to go ahead and do a quick share screen. And in this presentation, I'll be using everything Jupyter and everything Python, because those are the tools that I use the most in my work. So this was joint collaboration with the Callisto project. Through this program, we support teachers and students in grades 5 through 12 to get started with data science and data literacy. And as our main platform, we use Jupyter Notebooks and the Python programming language. Okay, now the theme of my talk is supporting cross-cultural understanding through code and Jupyter. So I want to motivate or want to share why I feel interested about doing this work. I was born in Mexico and I didn't move to Canada until I think something like 6 or 7 years ago. And in Canada, I learned that like in Mexico, there is a problem with the way our Indigenous communities have been mistreated and marginalized. I learned that in Canada, a recent initiative to do reconciliation has started. And I know that there's a lot of pain that has resulted from residential schools that cannot necessarily go away by doing reconciliation. But I believe that through reconciliation, we can take steps towards understanding each other and understanding Indigenous communities better. So I see a lot of potential in using open source tools like Python or Jupyter for this work, and my hope is that this will spark some motivation. So I want to walk you through some of our collaborations with one particular nation located in Agaikson, also known as the Powell River area. This is located in BC. I reside in Vancouver, which is a few kilometers away. And this collaboration started in 2018 when two Simon Fraser University professors, where I studied, visited the Tla'amin Nation to discuss the potential to collaborate. And so as part of that discussion, the idea was to explore the geometry behind traditional basket weaving. There's a lot of complexity involved in this. Typically, the wood that is used is cedar, and permission must be requested before using cedar root. And then from there, if permission is obtained, the cedar root is soaked for several days and then woven into these baskets. And the darker colors, so the darker colors are obtained through using cherry bark. So that means the pattern is woven into the basket as opposed to painted. So as part of the collaboration, the Tla'amin Nation provided pictures of these baskets, and then two developers along with myself worked together on this project. And our goal was to write some Python code that would model and showcase the mathematics behind these patterns. So the main math involves geometry and operations such as reflecting and symmetries. So that's what we tackled. So the model we recreated with Python looks more or less like this. And you'll see that each of these squares represents in our model one of the coils. And we try to use similar colors. Now, of course, some of the information is lost. We did experience some distortion, but it was a prototype that the nation was fairly excited with, and we were very excited with, as it represented one step towards representing or showcasing the math and complexity behind this process. So it's time for a mini demo. Before I jump in, let's go. So we worked with the notion of atomic motifs, or the smallest unit we can break down a pattern such that when we apply these operations, we can recreate the original pattern. So in this case, we can reflect a couple times and recreate that pattern you saw in the front of the basket. And then from here, we can do things like saving the pattern and then visualizing by using Python. In this case, we use matplotlib and a couple nested for loops. So in this case, the program or the script is not optimized, but it did a pretty good job at showcasing the geometries behind and simulating. Now you think one of the funky things that happen to us is there's this, some of the patterns will sort of deform or skew the basket. So there's still some work to be done with respect to improving how this works and making sure that the pattern don't skew the way the baskets look. But it is ongoing work. It was a fairly fun activity to work with. Okay, so then the next thing that I want to showcase with you, once I've shared this, is a collaboration done with Lamination once more. And this time our focus on 2020 and 2021 was to explore a tradition known as fish traps. These involve modifying the intertidal zone of the beach. And we focused on one particular type of beach or one particular type of trap called the crescent element, which has a semicircular or sometimes completely circular stone wall. So we use Python to generate an aerial view of the animation of the trap. So you can see in blue the water or the tide goes up, and the red dots represent the fish, and then the black dots represent the fish swimming inside the trap. At some point when the tide goes down low enough, then it's possible to go and harvest the fish. So then we went ahead and generated another Jupyter notebook with our trap simulations. In this case, we are taking real tide data obtained from Oceans and Fisheries Canada website, and then we visualize the beach. So in this case, we can set the parameters, the radius, the height of the trap, and the location. And it really got me thinking about all that was needed to generate these traps. It was necessary to consider the slope of the beach, the location of the beach relative to the behavior of the tide, and then also knowledge about when during the day or even during the year should the harvesting be done to get fish. And one thing that really caught my attention was the observation by the nations that this has been done for hundreds of years, which means that it indicates or implies that the harvesting is done in a sustainable way. So then another question we asked is, well, can we simulate what happens when we get greedy and when we build traps that harvest as much fish as possible? So we used Python and Jupyter to implement one variation of the Rickers model that uses even year and odd years pink salmon population. These even and odd year populations don't interbreed, so we can observe how the two do over the course of time. And so through Python and Jupyter, then we can go ahead and observe what happens when we get greedy and start harvesting. So we see that if we start off by harvesting a little bit of fish, just whatever our community needs, both populations survive. If we dial that up a bit, we see that within less than 10 years, it's possible to kill one of the two. One of the other populations thrive. And the reason for this is because as the odd year in this case dies, there's more resources for the even one. But we see that if we dial up this even more, it's possible to kill populations within 5 years. And this did turn out to happen at the Tla'amin Nation with the herring population. Once industrial fishing was put into place, herring population was wiped. And thus, the Tla'amin Nation was not able to harvest this for their communities. Now, one of the things that we are hoping to bring out as part of this is videos using drone footage of real fish traps, courtesy of Tla'amin Nation, all rights reserved by the nation, and also showcase how the traps still work. One of the things that our Callisto team is working on is a lesson plan for teachers and students that will include and showcase the engineering complexity behind these, along with some of these videos. So that's it for me. I hope this was an enjoyable talk, and thank you very much, PyLadies, for having me as part of this event.